Alright, we're going to look at Ohm's law today. So this is going to be our circuit. We've got a negative terminal of our battery and a positive terminal. We're going to signal that with two lines. And then we've got our wire going around. Forgive me, I am in a vehicle, so this is very squiggly, but here's our resistor. We're going to do a little zigzag for the resistor and close the circuit. So Ohm's law goes current times resistance equals voltage. And I is current, R is resistance, V is voltage. So for current, in these circuits, the electrons are actually going to go from negative to positive, but once upon a time, people were stupid and did not know that electrons existed, so they went by positive charges. So conventional current is going to go the other way, from our positive terminal to our negative terminal. So this is I, current. Voltage has to do with our battery, and resistance has to do with our resistor. The lower the resistance, the faster the current, at a constant voltage. So we can do some interesting things with this. We can do some algebra. So let's say that this voltage is 20 volts, and this resistor is 2 ohms. Ohm is just the unit of resistance. So what if I want to solve for the current? Then I say, instead of V equals IR, I can solve for I by dividing both sides by R. Here's I equals V over R. So that's going to be, in this case, 20 over 10, which is 2. Simple enough, right? But what if I want to add to this circuit and make it more interesting? Well, we can put the resistors in series. And in series just means they're next to each other, and the current can only take one path through the both of them, or through the multiple of them if you have more than two. So let's say that I know that this resistor is 2 ohms, and this resistor is 4 ohms. And I know that the voltage is 20 volts. I'm going to make it the same. What is the current? Well, in order to solve this, we have our V equals IR, Ohm's law. But the problem with this is that if we pick one resistor, we can't do that. That kind of violates the law. So we have to turn both the resistors into one big resistor, or one equivalent resistance. So for equivalent resistance in series, the law is that we have our equivalent resistance equals each of these added together, R1 plus R2, etc. So in this case, our equivalent resistance is going to be 2 ohms plus 4 ohms, which is going to get us 6. So I didn't pick very good numbers, because when we go to solve V equals IR, we're going to solve it for I. Just like last time, we're going to divide both sides by R equals V over R. So that's going to get us 20 over 6, which is equal to 10/3. Yeah, not very nice, but I'm making these up on the spot. So that is resistors in series. We can also put our resistors in parallel. So in parallel looks like this. It means that the current splits its path in two, and it can either pass by one resistor or it can pass by the other, or others, depending on how you build your circuit. So we're going to start with 2 resistors just like we did last time. And we're going to make them 2 and 4 again, just to show how the effects of parallel and series are going to work. And this time I'm going to say we know the current is 10 amps, and I want to know the voltage of this whole circuit. So in order to do this, just like last time, we need an equivalent resistance. So for parallel resistors, our equivalent resistance is going to be weird and fractiony, so 1 over Req is going to be equal to 1 over R1 plus 1 over R2, etc. So in this case, 1 over our equivalent resistance is going to be equal to 1 over 2 ohms plus 1 over 4 ohms. So now we need to do a bit of solving. So in order to get Req by itself, eventually I want to multiply both sides by Req. But before I do that, I want to make the right side of this simpler. And the way that we do that is to combine these fractions into one fraction. So if we have a half and a fourth, hopefully this example is simple enough that we know that we can turn halves into fourths. That's called using a common denominator. So we're going to say that 1 over Req equals 2 fourths, which is the same thing as a half, plus 1 fourth. So now that we have them both in fourths, then we can say that 1 over our equivalent resistance equals 3 fourths. So now we need some old elementary school math skills to come back into our brains. So we want to multiply both sides by REQ, so we can do that easily. So I'm going to take this and put it over here. We're going to multiply both sides by REQ and say that 1 equals 3/4 of our equivalent resistance. But now we need to get this by itself. And the way that we get this by itself is we divide both sides by 3/4, so it like disappears from that side. And dividing something means multiplying by the reciprocal. The reciprocal just means you flip it. So 4/3 is going to be our answer. 4/3 ohms is that equivalent resistance. But that's not what I asked. I asked what's the voltage. So now we have to take our Ohm's law, V equals IR, and say that this is I is 10, and we multiply that by 4/3, which is our R. I just messed that up. 4/3, not 4 over R, equals 40/3. Yeah, again, not very nice. But that's how this works. We can actually combine these things to make it even more complicated, so we can have resistors in parallel and in series at once. So let's say that here I have this resistor, and then I can divide the path into these. I'm making 3 because we're ready for complicated stuff, right? And the circuit will close here. So I want to know the value of this resistor that I'm going to outline here in purple. We're going to call the resistance X. The other resistors I'm going to give values. So this one is 5, and this one is 2, and this one is 6, and I have not thought this through, so it's very likely that X is going to end up being an ugly fraction, but our circuit's current total going around the circuit is going to be, I don't know, let's call it 4. And our voltage is going to be, let's see, we can make it 30. Okay, so now we're ready to solve for X. And this looks really complicated, but the way that we're going to do it is we're going to treat all these resistors like one equivalent resistor and work backwards. So we can use for the entire circuit, not for X, but for the whole entire circuit, we can do V equals IR. And to get R by itself, we need to do divide both sides by I, so R equals V over I. And this is 30 over 4. And that's going to simplify to 15 halves. So the total equivalent resistance of this entire circuit is 15 halves. So now we say, okay, how do we get to X? Well, we have a series, and then inside the series we have parallel. So first, I want to get the equivalent resistance of all this, and then we'll work inside the parallel. So I'm actually going to do this. I'm going to outline this in yellow and this in yellow. And I'm going to say that 15 halves, which is our total resistance for this, equals 5 plus R. And I know I'm using R like interchangeably. I don't know, let's call this RP for R parallel. So this is RP. So if we subtract 5 from both sides of this, I'm going to keep everything in fractions because I don't like decimals. Fractions are easier to work with in these things because then when we multiply by the reciprocal, it's like simpler. So 15 halves minus 5 is going to be equal to our parallel resistors. So 5, we have to put 5 into the denominator of 2. So we're just going to multiply 5 by 2. And we're going to put 2 underneath. So like we're multiplying it by 2 over 2, which is the same thing as 1, which is like why we're allowed to do that. So we're going to put like times 2 over 2 here. So that's going to allow us to get 15 halves minus 10 halves equals our resistance. And this is going to actually get us 5 halves. And again, we can't really simplify this or do much with this. So now we want to solve for our X, and we can use this ugly little formula that we had before. which is going to be the 1 over R EQ equals 1 over R1 plus 1 over R2 plus 1 over R3, right? Because this time we have 3. So in this case, 1 over REQ is equal to 5 halves. So we have 1 over 5 halves. So remember when I said divide by something equals multiplying by the reciprocal? So 1 over 5 halves is actually going to be 2/5. So we can replace this with 2/5. And if this gets confusing, pause the video, go back and listen again. So this is 2/5 equals 1 over, and we're going to call x R3. So we're going to say 1 over 6, and it doesn't matter the order because we're adding, plus 1 over 2 plus 1 over x. So now all we have to do is solve this equation for x. So the best way to do that is to get 1 over x by itself, and then we're going to get x by itself. So we need to put 1/6 and 1/2 into the same thing to get it on the other side. Or actually, no, what we're going to do is we're just going to subtract everything. So we're going to say 2/5 minus 1/6 minus 1/2 equals 1 over x. And the reason why I did that is I don't want to just find a common denominator for 6 and 2. I want to find a common denominator for 6, 2, and 5. So now I can put this up here, and I want a common denominator that is 6, 2, and 5, and that's going to be 30, right? Because 5 times 6 is 30, and 15 times 2 is 30, so there's a 5 and a 6 and a 2 multiplying into 30. So we can just multiply everything basically by whatever gets the bottom to 30. So for example, 2 over 5 we're going to multiply by 6 over 6. So 2 times 6 is 12, and 5 times 6 is 30. And then for 1/6 we're going to multiply by 5 over 5, so that's going to get us 5/30ths. And for 1/2 we're going to multiply by 15 over 15, which is going to get us 15/30ths. And this is going to be equal to 1 over x. So 12 minus 5 minus 15 equals 1 over x. Now, I'm going to stop this right now and say I picked bad numbers. I picked numbers that don't make sense and don't exist, apparently. Which is possible if you're making things up on the spot. So we're going to get a negative resistance, and that's not possible in the real world, but it's possible in math land. So 12 minus 5 minus 15 is going to be negative 8 over 30 equals 1 over x. So now all we have to do is just flip both of these. We could do something called cross multiplying, which is where we just multiply, or we divide both sides by each of these things, and then we end up like multiplying by the reciprocals. So in any case, we're going to get x equals negative 30 over 8. So that's how many ohms x is. So very long process, and we got a impossible number, but that's how you do it when you have a complicated problem like this. The last thing I want to go into is what happens to the current and the voltage in each of these situations with parallel and series. So we're going to go back to simple circuits with parallel and series. So we're going to start with 2 resistors in series. We're going to call them R1 and R2. We're not using numbers right now, so R1, R2. And each of these has its own voltage, so we're going to call it V1 and V2. And this is the difference in potential energy per charge across each of these individual resistors. Like if I take a voltmeter and I connect it like here and here, that's going to be V1. And if I take a voltmeter and connect it here and here, that's going to be V2. We can also have individual currents for each of these resistors. So we can have an I1 and an I2, and that's if we put an ammeter like right in the middle of one of these resistors, we would get like I1. Or if we put an ammeter here, we would get I2. So I want to know, like, is there a formula that we can use to get V1 and V2 or I1 and I2 without thinking too much about it? So if we look at this logically, we have an electron. It's going around the circuit, right? It reaches the first resistor, and when we're looking at resistors, we kind of pretend the rest of the wire doesn't have resistance. So as it's gone through the wire so far, it has not lost any potential energy. And let's say it's 1 coulomb of charge, so the voltage is the same as the potential energy. So then it goes across resistor 1, and it loses a certain amount of potential energy. And then it goes across resistor 2, and it loses another certain amount of potential energy, and then it gets back to the end. And when it gets to the end, it should be the voltage of the entire circuit, right? And so if the wires don't contribute to this, it makes sense that voltages are additive. So the law for this is going to be that V, we're going to call it V total. I know physicists love subscripts, so V total equals V1 plus V2, etc. And that's going to always be true when you have resistors in parallel. Or not parallel, series. In series. I meant series. Okay. Don't get messed up because of me. We're also going to have a law for current. And current is going to actually be the same across each of these resistors. Because if you think about it, current is charge per time, right? How many electrons or how many coulombs of charge are flowing through a given area of the circuit per second. And you could think of this kind of like a road in traffic. If you have one road and it goes in a circle and none of these cars can go anywhere else, if you measure the traffic at any given point, it's going to be the same if the cars are all backed up. Because whenever one person goes, the next one goes, and the next one goes. And that's the way that this is going to work, is that at any given time, you're going to have the same current flowing through here and here and here and here and here because it has nowhere else to go. You can also think of it like if you have water flowing through a hose. Like if you're going to measure the velocity of water at any given point in this hose, it's going to be the same. So you're going to have your I total, which is here, equals I1, which is equal to I2, which is equal to I3, or whatever other currents you have in here from resistors. So that's for series. So now let's look in parallel and see if we can find voltage and current laws in parallel. So again, I'm going to try to keep this simple, and I'm going to draw a circuit with only two resistors in parallel and nothing else. Alright, so this has, again, a total voltage and a total current. And we're not worried about the equivalent resistance, and the reason why is because we already figured out how to do that. We already went through that, so we're just looking at voltage and current and how they relate when resistors are in parallel and series. So each of these, again, has a V1 or V2 and an I1 or I2, right, because they are R1 and R2. So for this one, current is going to be additive. And the reason why is because, like, again, it's charge per time, but now your cars and the traffic or your water in the hose has two different pathways that it can go down, but you're not bringing anything else into the circuit when you split this current. So logically, these currents should add up. So if I have like 10 amps going in, I can split it into like 3 amps and 7 amps or 6 amps and 4 amps, as long as it adds up. So if you get a current, if you add up the currents in this parallel circuit and they add up to too much, it's wrong. So that's going to be our law here, is I total equals I1 plus I2. So it's adding. The voltage is actually going to be the same across each of these resistors, because if you think about it, voltage is the difference in potential energy per charge, right? So our electron at the beginning has got like a certain amount of potential energy. It goes through the wire, and again, in this theoretical environment, we're pretending the wire like doesn't have any resistance whatsoever. So we don't lose any potential energy until we get to our resistors in parallel. And again, we have like a branching off, and our electron can go one of two ways, but whichever way it goes, it gets to the resistor, and right before the resistor, it has the same potential energy it did at the start of the circuit. And right after the resistor, it goes through the wire, and gets to the positive terminal of the battery, right? And all that through the wire, again, is not losing any potential energy because the wire is perfect, evidently. So the point is that the only place that we're changing voltage is this one singular resistor, because the other resistors were not in this electron's path. So all these voltages are going to add up, because all these electrons are going to experience this exact same thing we just talked about, where they only go through one resistor. So the voltage across each of these resistors has to be the same, or else this wouldn't make any sense. So it's going to be V total equals V1 equals V2 equals any other voltages and any other resistances in your circuit. So, for example, if I were to have a problem here with resistors in parallel, now instead of asking about the resistance or about the current and voltage of the whole circuit, I'm going to ask about what is the current in one of these resistors. So the first resistor, we're going to make 2 ohms. And again, if we get a bad number, it's because I'm making this up on the spot, not because we miscalculated. So we have a 2 ohm resistor, we have a 4 ohm resistor, and we're going to have a voltage in this entire circuit of 20 volts. So the current in, actually no, we're not going to give either of the currents, but we're going to figure this out. So if the total if the total resistance of these 2 resistors is 1 over R EQ equals 1 over 2 plus 1 over 4, right? So we're going to get the whole resistance, and the reason we're getting the whole resistance of these 2 resistors is we're going to get the current. And when we get the current, then we can use that current to say, okay, these 2 currents have to be the sum of the total, or not, they have to add up to the total current. So 1 over 2 plus 1 over 4 is going to get us 3/4, which again gets us the ugly equivalent resistance of 4/3. So now we know that our like equivalent resistance of both these resistors is 4/3. So then by V equals IR, we can say that I equals V over R. So the current is going to be equal to 20 over 4/3, and remember, dividing is multiplying by the reciprocal, so 20 times 3/4. So 20 times 3/4 actually gets us a like regular integer. It gets us 15, right? So now we know that the current around the whole circuit is 15 amps, and because of what we just learned, we know that these 2 currents in the resistors in parallel have to add up to 15 amps. So 15 equals I1 plus I2. Now I gave you each of these resistances, and we also know that the voltage across each of these resistors is 20 volts, because in parallel, voltage across each resistor is going to be the same as voltage across the whole circuit. So now we can actually use V equals IR for these individual resistors in order to figure out what the current is. So actually, we didn't even have to figure out the whole current. We can just use V equals IR and say that 20 equals I times 2 and 20 equals I times 4, right? So then I'm going to call this I1 for the 2 ohm resistor is going to be equal to 10, and then I2 for the second resistor is going to be equal to 5. And so we did not need to find this. We didn't need to do this math in order to do the whole thing. But you can see now that 10 and 5 add up to 15. And so that's kind of a proof of what we just learned. So hopefully now you have a good idea of how to work these circuits, and you can try some of these problems on your own. And you can do basically what I did and just make up numbers and make up circuits on the spot. So you have infinity of these problems at your disposal. So get solving.